Okay, so the last video we talked about how non-aromatic compounds want to react to become aromatic, and anti-aromatic compounds want to react to become non-aromatic. The one thing we haven't talked about is, are there reactions that we can do where we have aromatic starting materials? And it would seem like the answer would be no, right? Because aromatic starting materials are already stable. Any reaction we do to them, especially if it breaks aromaticity, is just going to be bad news, right? Wrong. It turns out that there are ways that we can do ways ways that we can get aromatic compounds to react, um, and but it takes some work. So let's talk about those things in this video, and we'll learn some new reactions. All right. So we've said before that if you take benzene and react it with Br2, you get no reaction. Right? We don't get the addition to the pi bonds. We don't break the pi bonds in there, and this makes sense, right? If this is an aromatic starting material, we would not expect to see the addition of bromine across one of those double bonds, because that would result in a non-aromatic product. Right? And so this doesn't work. Right? Aromatic to non-aromatic is not a favorable reaction. But what it turns out you can do is you can take a compound, or you can take benzene, and you can react it with bromine. You have to add a catalyst, which is iron tribromide, FeBr3 and Br2, and you will get a reaction. And that reaction is not the breaking of one of the pi bonds, but instead just a substitution where the bromine replaces one of those hydrogens. And notice here that we are going from an aromatic starting material to an aromatic product. And this is the key, right? We're not going to ever really have reactions that start with an aromatic system and result in a non-aromatic system. It's always going to be going from aromatic to aromatic. Okay, but the question is, how does this work? How do we end up with a bromine here and replace a hydrogen? So this is a reaction called electrophilic aromatic substitution, or EAS. You've done this reaction if you've been in, if you're in the organic 2 lab, you've done this reaction. Nitration is an example of electrophilic aromatic substitution. The Friedel-Crafts reaction is an example of electrophilic aromatic substitution. So we have a couple of these in the lab. So you may have seen some of these mechanisms, some of this before in the lab. We're going to treat it a little bit more. We're going to talk about it a little bit more here. The nice thing is that every version of electrophilic aromatic substitution always has 3 steps, and they're always the same step. Step 1 is we have to activate the electrophile. Okay, this is the E in EAS, electrophilic, and what this is Br2 is an electrophile, but it's not a very strong electrophile. It's good enough for reacting with your garden variety double bonds, but it is not nowhere near strong enough to react with things like benzene, right? That's aromatic and already stable. So we need to make a really good electrophile, right? So we're going to activate the electrophile and make it super electrophilic. And the way we do that is the bromine adds to iron tribromide. It just shares its electrons with the iron and makes a positively charged bromine and a negatively charged iron. Now, we've really only seen positively charged bromine once before. If you think back to organic 1, when we did the addition of bromine to double bonds, you have the bromonium ion, the 3-membered ring with a positively charged bromine in it. And one of the things we talked about with the bromonium ion is how reactive that Br plus is, right? It's a really great leaving group. Bromine doesn't like to have positive charge on it, all this other good stuff. And so, of course, what we've done is we've made a fantastic leaving group. Right? This whole thing over here is a really great leaving group. Fantastic leaving group. And what that means is that now this bromine is ready to be attacked by a nucleophile. You have to heat these things up to get this to go because the benzene is so unreactive. But when you have a good enough electrophile, benzene will react with the bromine. The pi bond will come attack that bromine and kick off this leaving group, and we're going to make a carbocation. This is step 2 of every electrophilic aromatic substitution. Right? Your aromatic ring attacks the electrophile and makes a carbocation. Right? Pi bond attacks the bromine. We break the pi bond, which creates a carbocation, and notice that now we have a non-aromatic intermediate here, right? So we've gone from aromatic to non-aromatic. This is not a favorable step, right? The good news is that we're going to get back to aromatic by the time we finish this reaction, right? If we just stopped here, this reaction would never go anywhere because aromatic to non-aromatic is not a favorable process. The only reason that we can get this to go is because this leaving group is so stable that once it leaves, it's pretty much unreactive. And so the reverse reaction to restore the benzene ring and take away the bromine is very, very hard to do. Okay, so we add to our electrophile. We create our electrophile in step 1. We add to our electrophile in step 2. We end up with a carbocation. And this carbocation, so now we've got non-aromatic carbocation. And what do we know about non-aromatic starting materials? They want to make aromatic products, right? And so to do that, we need to get this neutral sp3 carbon to be a part of a pi bond. So how do we do that? We do that by elimination. So step 3 is an E1 elimination to make an aromatic product. All right, so we don't need a particular base in here because this carbocation is so reactive, non-aromatic to aromatic product. We don't even really need a base at all, right? We could have something like FeBr4 minus or whatever. Something comes in, takes this hydrogen, does the elimination, and gives us our aromatic ring back. But notice that it leaves the bromine behind, right? We don't have to use the bromine to make the elimination happen because we have that carbocation there. And so we get this aromatic product that looks like our aromatic product up here, right? And this gives us our electrophilic aromatic substitution. More examples of electrophilic aromatic substitution coming up in the next video.